To reach another star, we must first survive a trillion-kilometer graveyard of frozen giants. For decades, humanity has been sending spacecraft deeper and deeper into the darkness. Voyager 1 and Voyager 2 proved that machines can survive billions of kilometers from Earth. But the journey to another star would expose a much more difficult problem: distance on a scale our current spacecraft were never designed to endure. Voyager is now traveling through interstellar space, but compared with the full architecture of our solar system, it has barely begun to leave home. The Oort Cloud is believed to surround the solar system as an enormous three-dimensional shell of icy bodies. It isn't a neat ring like the asteroid belt. Objects could exist in every direction, stretching outward for hundreds of billions, potentially trillions, of kilometers. And that changes the engineering problem completely. A spacecraft traveling toward another star wouldn't simply be crossing an empty road. It would be entering an enormous volume containing ancient frozen material left over from the formation of the solar system. Most of these objects would be incredibly far apart. So the danger isn't that a spacecraft would constantly slam into ice. The real danger is probability. At interstellar speeds, even a tiny particle can become catastrophic. A grain of dust that would be harmless to a spacecraft moving at ordinary speeds can release enormous amounts of energy when struck at tens of kilometers per second. A larger fragment could punch through shielding, damage electronics, destroy instruments, or compromise the spacecraft before anyone on Earth even knows something went wrong. Voyager gives us a powerful lesson here. Its mission was never designed around surviving a high-speed passage through a trillion-kilometer deep space environment. Its systems were engineered for longevity, but not for the kind of extreme velocities and impact hazards envisioned for true interstellar missions. And that is where the next generation of propulsion becomes critical. By 2026, Breakthrough Starshot milestones and related interstellar research provide a useful baseline for thinking about what a future starship might require: extraordinary acceleration, extreme velocity, autonomous navigation, and a structure capable of surviving an environment where communication delays make real-time control impossible. Starshot's basic concept is radically different from Voyager. Instead of slowly accelerating a massive spacecraft with conventional propulsion, the concept uses an ultra-light spacecraft pushed by powerful laser beams. The objective is to reach a significant fraction of the speed of light. That speed could eventually make journeys to nearby stars measured in decades rather than thousands of years. But speed creates a brutal trade-off. The faster the spacecraft moves, the more dangerous every particle becomes. A microscopic impact at a fraction of light speed is no longer a minor engineering inconvenience. It becomes a high-energy collision. That means an interstellar spacecraft may need layers of protection rather than a simple metal hull. Engineers could require sacrificial shielding at the front of the spacecraft, materials capable of dispersing impact energy, redundant electronics, protected instruments, and autonomous systems capable of detecting and responding to damage without waiting for instructions from Earth. And then there is endurance. A mission traveling toward another star could operate for decades. Its power system would need to function long after launch. Its computers would need to survive radiation. Its communication system would need to remain operational across distances measured in light years. This is why nuclear power becomes so important to the broader interstellar propulsion discussion. Solar energy becomes dramatically weaker as a spacecraft moves away from the Sun. Nuclear systems, by contrast, can provide a long-duration source of energy independent of sunlight. But propulsion, shielding, and power are only pieces of the puzzle. The deeper we travel, the more important autonomous navigation becomes. Imagine a spacecraft millions of kilometers from Earth, moving at enormous velocity, encountering an unexpected fragment of debris. There may be no time to ask mission control what to do. The spacecraft would have to recognize the threat, calculate its trajectory, determine whether it can maneuver, and protect itself automatically. And this brings us back to the Oort cloud. For the first time, we have to stop imagining the solar system as a collection of planets surrounded by empty space. Beyond the planets lies an enormous gravitational domain. Far beyond Neptune, countless icy remnants may orbit the Sun on immense trajectories. Some could take thousands or even millions of years to complete an orbit. The Oort cloud is therefore less like a wall and more like a gigantic three-dimensional ocean of ancient debris. A future interstellar spacecraft would not necessarily have to weave through a dense field of objects. The distances between individual bodies may be enormous. But the journey would cover such an immense distance that even extremely rare encounters become part of the risk calculation. And at interstellar velocity, the smallest objects matter. This is the paradox of interstellar travel. We need to go faster because the stars are unimaginably far away. But the faster we go, the more dangerous the space between those stars becomes. Voyager taught us how to survive the slow crawl into deep space. The next generation of spacecraft must teach us something far more difficult: how to survive deep space while moving fast enough to actually reach another star. Because the greatest obstacle between humanity and another solar system may not be the distance itself. It may be everything hiding inside the darkness between here and there. But surviving the Oort cloud is only the beginning. The real nightmare starts when we increase the speed. Imagine a spacecraft leaving the solar system at tens of kilometers per second. At that velocity, a collision with a microscopic particle can already become dangerous. Now increase that speed dramatically. The spacecraft is no longer simply traveling through space. It is turning space itself into a weapon. Every dust particle becomes a projectile. Every grain of frozen material carries kinetic energy. And because the spacecraft may be traveling for decades, even extremely rare impacts accumulate into a serious engineering problem. This is why an interstellar spacecraft could require a completely different philosophy of protection. Instead of building one enormously thick wall, engineers could use multiple defensive layers. The first layer would act as a sacrificial shield. Its purpose would not necessarily be to remain intact. Instead, it could absorb the initial impact and break incoming particles into smaller fragments before they reach the spacecraft. Behind that could be another layer separated by a gap. This spacing is important. When a particle strikes the first shield at extremely high velocity, it can vaporize itself and part of the shield. The resulting cloud of fragments and plasma then expands outward. With enough separation, that energy can spread over a larger area before reaching the main spacecraft. This basic principle is already familiar from high-speed impact protection concepts. But an interstellar spacecraft would push the idea to an entirely different level. And there is another problem. You cannot simply make the spacecraft heavier and heavier. Every kilogram launched toward another star creates another enormous propulsion challenge. This becomes especially important for concepts inspired by Breakthrough Starshot. If the spacecraft is designed to be extremely lightweight, then adding tons of conventional shielding defeats the purpose. So the future of interstellar protection may depend on materials rather than mass. Ultra-light structures, advanced composites, layered ceramics, metallic foils, and other engineered materials could potentially provide protection without turning the spacecraft into a massive projectile that becomes impossible to accelerate. But even the best shield cannot protect everything. The spacecraft would need redundancy. Critical computers could be duplicated. Communication systems could have backups. Sensors could operate in parallel. Power distribution could be divided into independent sections. The philosophy would be simple: If one system dies, the mission must continue. Because there is one thing an interstellar spacecraft cannot afford: a repair crew.